Welcome everyone. In this lesson, we're going to see probably our most important integration technique. We're going to use it all the time in it helping us integrate functions in this course, and then even going into Calc 2 and later on into Calc 3. This technique, this integration technique that we're going to see is incredibly useful. And so specifically, we're going to see how to calculate an indefinite integral using substitution rule. All right, so first, let's talk a little bit about where this rule, where it comes from. And to kind of set the stage, let's remember back to derivatives. There's a relationship between differentiation and integration. And so we had this, one of our main derivative rules here was the chain rule, also very important. And what this was kind of telling us how to do is it was giving us a way, a method, a rule to calculate the derivative of a composite function. So that's what we had here in the chain rule. We are differentiating a composite function, f with g of x plugged in, or f composed with g of x. And so what the chain rule would say is you differentiate the outer function, you keep your inner function plugged in, and then you multiply that by the derivative of the inner function. So this is kind of our standard terminology here. We have our outer function, and our inner function in this case. And how do we know it's our inner function? Well, it's literally, g of x is literally plugged into, it's inside the parentheses for this outer function. All right, so that's how we would differentiate. So let's kind of think of it now. Let's write this out. So let's suppose we had this function capital F of u of x, and we wanted to differentiate it. What would chain rule look like? Well, it'd be the derivative of our outer function with the inner function plugged in times the derivative of our inner function. And so going through and calculating the derivative here is chain rule. That's what we've seen. And we know that when there's a derivative process going on, well, there's a question, can we work backwards? And so there's a question, if we were to kind of start with this more complicated looking expression, is there a rule or is there a technique that would allow us to recover our original function? And that's what we're going to see. The integration process, the technique that we're going to see is called substitution rule. Or maybe use substitution for short. So we're going to have some kind of complicated or more complicated function, and we're going to work back in some way to recover this original function, our original composite function. So that's what we want to keep in mind. We're dealing with composite functions. When we talk about chain rule and substitution rule, composite functions. So there's an inner function and an outer function. All right, so that means we're going to need a little bit of notation and terminology here to help us go through the process of substitution rule. And the gadget that we're going to need, and we're going to use this in other integration techniques as well, is this idea of a differential. So suppose u equal to g of x is a differentiable function. Then we define the differential du to be the derivative of g of x times dx. So essentially, if we have this function g of x, the way we calculate the differential du is we calculate the derivative of g and then multiply by dx. So we differentiate and then multiply by dx. So we have u equal to g of x. How does this look? We'll differentiate the function and then just multiply by dx, and that's calculating du. That's how this looks. And so these du and dx's that we have here, they're differentials, and just think of them as one whole thing. So think of this du as it's just one little piece of notation. You can think of it just like the name of a variable. So you don't think of it as d times u or anything like that. This is just the name of a new variable, which we call du. Same thing for the dx here. Don't think of it as kind of a d and an x separate. Just think of it as dx. Just one, the name of a variable here. All right, so a little example. Calculate the differential for this function u equal to x squared plus 1. So we're going to calculate this differential. And let's see how it looks. So we're going to calculate du. So differentiate x squared plus 1, we get 2x. And then multiply by dx. So we get 2x times dx. And that's all this 2x is it's just the derivative of the function here. And then we're just multiplying by dx. All right, so why is this going to be useful? Well, this differential is part of the way we work backwards. So we know we're trying to undo this integration technique that we're going to see. We're trying to undo the chain rule. And so here it is. Here's substitution rule. Here's the statement. It says if u equal to g of x is a differentiable function and f is continuous, f is a continuous function, then the integral that we're trying to do, which we have right here, we can do a change of variables. And that's really what we're doing here is a change of variables. So we're going to let u equal to g of x. And then we're going to calculate the differential. So it's going to be g prime of x dx. So let's look at the integral that we're trying to do. And what we're doing is a change of variables. So this g of x right in here, we're saying u is equal to g of x. So this g of x right here, that becomes u. So we're kind of consolidating this down so that the goal here is just to look at the outer function in some way. And then this g prime of x dx that we have right here, well, that becomes du from our differential calculation. So what we're seeing here is the g of x is our new variable u. And then this g prime of x dx, that's going to become our differential du. All right, so this is the setup. This is kind of what the rule says. We're going to think of it more as a process. The way we do the substitution rule, we're going to think of it more as a process. So ultimately, the goal here is we're trying to, in a lot of cases, we're trying to integrate a composite function. And what we have here is it takes a complicated looking integral. There's going to be a lot of things going on for this left integral. This is the one we're going to be trying to do. And what this substitution rule is going to do is it takes a complicated integral on the left and it gives us a simplified integral on the right, or an easier one on the right. So there still might be some work over here. This might not be entirely trivial, but it's going to be hopefully easier. There'll be less things to consider. All right, so let's see the process here. So this is the statement of substitution rule, and it's really we're doing a change of variables. So we're looking at our complicated integral, and we're saying, all right, let's let this inner function be u, and then we switch over the we need to switch over the differential. All right, so we'll see how the process works in an example, but for right now, there's the statement of our substitution rule.